Okay, here we are in the lab again, and welcome to episode 20. So in this episode, we're going to, well, we're at a point now, so we're done with the front end basically, except for some minor stuff that just will fall into place as we go. So we got to work on our data acquisition part of the board. I don't know if you want to call it the rear end, but it's the data acquisition section. And so it looks like the digital potentiometer chip is not going to work. The data sheet shows a +4, -4 supply voltage for it. And so I figured it was like an op amp where you just tie the negative to ground and you just lose some resolution. No, not in this case. It just doesn't work. According to ChatGPT, it might even damage the chip if you do that. So I'm going to pop the chip back off, scrap the potentiometer. I think I'm going to add in an analog switch because, well, we could add a different potentiometer, a different chip. There's all kinds, but I don't think we're going to need it. I think the DAC will be able to use at least one of the DAC outputs to control any like the base of the transistor or something. So I don't think we're going to need the potentiometer anyway. So I think I'll add an analog switch so that like you could do like a digital multimeter where you have different ranges. So you select your range with the analog switch. I'm thinking about doing that. In fact, I'm looking at some chips right now. And so we're at a point right now where we got to start setting up the modules for this. So this video is going to cover the DAC module and the PWM module. And we're going to look at, I haven't really talked about the Windows application program yet. So we're going to go through that. And that's going to take a little time, but we're going to see how the data goes through from Windows through the USB to mainbrain and then how it gets to the peripheral board. And that part we kind of covered a little bit already, but I want to show you how that's through. The data passes through and start getting acquainted with the Windows application because we might have to do some work in there. I don't know. We'll see. I'm going to be doing a lot of work in there. But and so we'll do that, and then we'll just go through the commands that set the variables for the PWM and the DAC. And then the next video, we're going to get into how to configure those in more detail, and they do a lot of more complex stuff we're going to get into in the next video too. But we got to start one step at a time. So this video, we're going to just look at data propagation through the system and the DAC and the PWM controls. All right. So let's get to it. Okay, so let's start off with looking at the Windows app for mainbrain. I haven't really talked about that too much. So that's this guy right here. So when you plug mainbrain in, let's go to Device Manager real fast. So when you plug mainbrain in, then it pops up under the USB devices. So pops up as mainbrain MZ. And so it registers with Windows automatically when you plug it in. So then when you start the application, it searches for this GUID right here. And when it finds it, it lists it, and they can list more than one. And then in that case, you have to select which one that you want. because you can have multiple main brains connected to the host computer at any given time. So then it says press any key to connect. So you just hit a key. All right, so main brain is connected. This is the voltage, the supply voltage that it's running on. It can go up to 24 volts. Actually, a little more than 24, but 24 is like the maximum recommended for my spec. And then it shows how much current that the board is taking, and that is total current. So any peripherals connected and running, like we have the I/O board right now, that also is reflected here in the total. So it's not a lot, but it's some. And that's the display. 100 milliamp of this is the display right now, give or take, depending on your brightness setting. All right. So then come up here and hit utilities. So this is what we have, and I don't have all of this available finished yet, but to test the connection, I need to change that with to main brain. So this is the USB connection here. So if you just double click on that, all right, so we have success, but obviously we have a connection because we're getting data transferred here. The only thing for right now is that we'll do the peripheral commands because we're working with the I/O board. So double click on that. All right. So then you have a choice. You can just send a data byte to the I/O board. And when you click on that, then you select the board address and then what the data byte you want to send. So you could, it's decimal. So you might want to send 34, and then you just double click it and it will send it to the I/O board and display this 34 on the LED port of the I/O board. All right. The build board list, I'm still working on that, but two of the items that I've added is set the DAC. So you can send an output, it's a 16-bit output you can send to the DAC, or you can set the PWM, the frequency and the duty cycle, both 16 bits. And so we'll take a look at that. So let's send a byte to the board and see what we get. So we'll just do like 87. Let's do 187. Because we can go up to 255 for our 8 bits. So we'll go 187, and then we'll double click on it, and then we'll send it, and then you can see that it's 187. Now if we take a look at the DAC utility, so the DAC can't go to 0 and it can't go to 3.3 volts. There's a range. So the variable range is a minimum of 205 to 3890. So if we put 3890 in there and we double click, that sends it out. So that's the maximum. So as you can see, the level of the DAC is like 3.1 something volts. So that's the highest you're going to get out of it. All right. So then if we just go 0, I have the firmware set so it can't go outside of the range. So you can set it outside of the range, but the variable written to the actual DAC is not outside that range. So we can just go 0 and watch what happens. So you can see it doesn't go absolutely 0, but it's at like 220 millivolts. All right, so that's our range. All right, so then later I'll calculate the voltage, and we'll just set the voltage here. We could even do a slider or a knob or something, but anyway, we're going to set the voltage instead of this number later. But right now, this is what we got, the first step. So then if you want to go like somewhere in between, would be like 15 or 1600, right? Double click. All right, so we got 1.22 volts. Yeah, sounds about right. 2000, let's go 2500. And there you go. Voltage is 2.6 or 2.0 volts, right? And so that's pretty much the DAC control. So we'll go over how it works, I guess. We'll do the PWM next. So real fast, and then we'll get into more detail about how it works. So let's jump over to the board and move our probe over to the PWM output. All right, let's get a probe moved here. Now I got to get it on there where you guys can see the LEDs. It doesn't really matter, but gives you a view of the board besides the probe. Huh? All right, so that's pretty good. So that's our probe. And as you can see, we have a PWM. So now we'll jump over to the PWM. So then we have the period and the duty cycle. So the way it works, the period sets the frequency basically. And so the lower the number, the higher the frequency. So during our initialization, we set this at 1000 or 2000. We set this at 2000, duty cycle at 1000, which makes it 50% because it's half. All right. So 2500 will make it a lower frequency, and we'll do our duty cycle at say 1000, and then we'll send that on over. And you can see that it changes frequency and it goes down, and the duty cycle changed too because it's not exactly 50%. So then if we make this 2000, the frequency will go up slightly and the duty cycle will be 50%. All right, there you go. So we're running at about 418 kilohertz, and we can bring that way down. We can go like 5000 here. And I'll change the setting on the scope to pull it up a little better. There you go. So now it's 167. And so we can go like 10,000 and just on and on. And so we could go like let's see, let's go like 1200. All right. And see, you can see that we made the duty cycle the opposite. All right. So it's on more than it's off. And so half a duty, 50% duty cycle would be 600. So we can hit 600, double click, and there we go, 50% duty cycle again. Okay, so that's basically the control of the PWM, the basic. All right, it's going to get way more complicated, but we'll go through the code real fast, how this works, and then we'll discuss what we can do with this. Okay, so let's pull up our code for the app, the Windows app. So when we're right here and we select utilities, then it loads this list. And then when you double click on a command, then it brings up another list. So that's this list box right here, the peripherals list box. So this is under IDC programs, under the command, WM command. All right. So when you select, this list box gets loaded here, and then it sends a command based on the index. So on the peripherals one, which is here, then when you click on it, then it shows these things right here, your edit box and your static text. All right. And different ones show different things. So you hide some and you show others. And there'll be more stuff too. It's going to get a lot more busy. All right. So we're on set DAC. So that is case number 2. All right. So it shows that. And then when you double click, that's when it sends the data. So then it sends a command with the index plus 100. So the first list is just regular whatever index it is. But then on this list, then it is the index plus 100, just to distinguish it as being a different list, right? So if I do control and click on here, then we come down to our command. So all the commands from the list box goes through here. And I have a lot of straightening up to do in my code, but you get down here to right here. So then it's the index plus 1, so that you don't have an index 0. So that propagates all the way through to the 100. So when you get index 100, it's actually 101. All right. And so he comes down here, and actually, I don't need this in here anymore. Or do I? Yeah, I do need that in here. No, I don't. We can take this out while I'm here. Just delete that. That's the way it was before I added it in. All right, so I'll just build this. Oh, I can't build it because I got it open. All right, so this is the peripherals utility section. And so we are on set DAC. So this is set DAC here, index 103. So when you double click on it, that's when it sends this. So it gets the Windows text, which is the address edit. So that's the address. So it gets the board address and then puts it in the board address variable. Then it gets the text from the output, the what you want to send. So it's a 16-bit. So it gets the word and converts it into a number. All right. And so then it splits the 16 bits into 2 8-bit bytes. So it gets split into 2 bytes. All right. And then it calls this USB byte out, which is a new thing that I just started. So I got to convert a lot of other code into this, but just for right now. So it's the command, which is this, but this is hexadecimal. You can go 103, whichever, it's the same. So you just give it you pass it the variable of the index, which is the command number, then the board address, and then the data you want to send. Now, the data is a 62-byte array. So you can, every time Windows sends to the USB, it's 64 bytes. So you pass that array to this function right here, USB byte out. So I'll control and click. So that's right down here. And so the out buffer, which is the array that goes out the USB, the very first variable is the command. So that tells MainBrain what command you want it to do. All right. So then you're passing the board address to MainBrain through the USB here, so that it knows what board it needs to write to, and which is what it dictates which part of the SRAM that it writes to. All right. So then the board data, we copy the board data from our buffer, our data buffer here. We copy that into our output buffer for the USB. And that's why there's only 62 bytes, right? Because 0 and 1 are already spoken for, because it has to be the command that you want to implement and the board address. And then the rest is data. So then you just call this Windows function WinUSB write pipe, and it writes 64 bytes. And if it fails, it pops up the message box. All right, and then it terminates, and hopefully, with any luck, your data arrived at main brain. All right, so that's how the data gets from the Windows app to the USB. All right, so it sends it out the USB on a pipe, which USB calls it a pipe, a write pipe. All right, so now let's go to main brain's USB code, and we will take a look at how that works. So over here in our main brain code, and I made the font a little bit bigger still so you guys can see it a little better. I'm still worried it's a little small. Looks like Flintstone writing, but it'll show up better on your guys' video, I think. All right, so it's in the USB code. There is a section. All right, so this is the USB handler, interrupt handler. All right, and so there's a function outside the USB interrupt handler that decodes the commands that you send it from the Windows app. All right, so there's different, all these are in the list of the first list box. And so then once you come down here, past 64, this 64 is where it sends the data for the voltage and the current. And then above 64 is our peripheral command section. All right, so this is case 65, hexadecimal 65, and that's command 0. That's where we send the byte to the board. So we set the current board address that we want to talk to, okay? And we get that from the receive buffer, because the host is the sender. We're the receiver. Main brain is the receiver. So endpoint 1. Endpoint 0 is reserved for commands. Endpoint 1 is receive. Endpoint 2 is for sending to the host. All right, so we receive it on, the board address is in the array position 1. And it matches over here in our array right here, because our board address here is output buffer array position 1. So they match. So whatever the output buffer position is here, it'll show up identically on the other end of the USB and main brain. All right. So then we want to write the data to the SRAM. And that comes from so we want the current board address. This is the calculation, because see, once we set the board address, then we can calculate the position in SRAM for the base address. So we take the current board address, which is 1. We subtract 1 from it so that we have a 0 through 7. We multiply it by the base address, because each board has this many bytes, 1K. All right, and so we write that to memory location 0. Or no, this is the memory location, and we write command 0. All right, so this is command 0, we write it here. So we write command 0 at this memory location, calculated from the current board address, okay? So then we got to do the data. So the data is the same address plus 1. And then that we read in the position 2 of the receive buffer into this SRAM location, all right? So then once we do that, we just set this flag. So when this flag is 1, it's kind of like Windows sends a Windows message to the operating system. So we set this flag, and in our main code, right here, our main program loop, we come down here and we check for a command request. So if this is set, which it would be if we send a byte, our data, then it calls this function and for the current board address, and then it resets the flag after it does that. So we'll do a control click, and we'll come down here. And so this is the command to send a byte to the peripheral. And you pass it the address of the board you want to write to. And then we set a timer here, because if there's no board in the system, it's not going to get any acknowledge back. And it waits for that acknowledge. So we set a timer, and we start the timer down here. And then we set the address of the board. All right, so we set the address of the board to address 1, which in our case, it's 1. We start the timer, and we wait for it to acknowledge. So right here, we just sit here and wait till either we get an acknowledge or the timer times out. So if the board is missing in the system, there's no board with that address, then it's not going to get acknowledged here. So it's going to wait for the timer to time out, and then it's going to either add it into our list, because we're going to build a peripherals list too. So that's coming. Or it's going to write a 0 to the list saying it's not there because the timer timed out. And then I do a little status check on MainBrain's LED to tell, so I know which occurred. And that's been proven, so I'm almost ready to take these out, the LEDs out. All right. So then we reset the timer flag to 0 so we can do it again later. And then since we got an acknowledge or a timeout, then we reset the board address to 0, and we stop the timer, and we're done. So either our board wasn't in the system and we timed out, or we wrote to memory and sent it command to the board to tell it to read that command from memory and execute it, okay? And then once we do that, the data should be in SRAM. So then we come over here, and as you remember before, this is our interrupt for our I/O board, and then it handles the command. So when we get that address selected, the board select, it causes this interrupt. Comes down here, it checks to see if it was a change notice. And if it is, then it checks to see if it went low or if it was coming high. So if it's coming low, that means we just got the request. So we read address 0 for the command. We display that command on the LED port. And then we check the command to see what it is. And if it's command 0, then we read the data from the SRAM address 1, which is offset 1 of the USB array, data array. But it might not always be the same, but it kind of lines up. And then we write, in this case, 0, we write the data to the LED port, which overwrites the data we just wrote, okay? So then, I don't have command 1 implemented yet. Command 2 is set to DAC, So when it gets this command, which is 2, then it reads memory location 2, sticks the data into a variable called my word, and so then we shift it left 8 bits, and then we read address 1 into it, and then add it to my word, and that forms a 16-bit value for the DAC. And then this is where it checks to see if your data falls within the range specified by the data sheet, and if it's outside, it makes it default to inside. All right. So if it's above F32 hex, then it becomes F32 hex regardless. And if it's below CD, then it becomes CD regardless. All right. So then it updates the DAC with your data and breaks out, and then comes down here, sends the acknowledge, and waits for the board select line to be taken off, and then it clears. And as we've seen in our previous video, that it completes the IO write cycle. So it's kind of a long way to do it, but the data does propagate from our Windows application into mainbrain and into our IO board, whichever one we want to write to. So we're starting to build it to where we can write to individual IO boards. We're just almost there. So now that we see how the data goes in there, then we'll have to look next, and I'll show you what kind of complicated signals that we can actually generate with the DAC and the PWM, and how we can use them both together at the same time. Okay, so it's quite a process to go from the application through the USB into mainbrain, into the SRAM, and then have the IO board read it. But as you can see, it's working good. It's reliable. No problems yet so far. Nothing serious. Got a lot of code to write still for everything. So now is what we have is the ability to generate a square wave. We can control the duty cycle, and we can control the frequency. All right. And then we can generate a voltage level, but with the D to A converter. And we can go from like 220 millivolts all the way up to 3.1 volts. So we can control it very precisely in between that range. So then the next video, we're going to look into more complex waveforms, because you can connect the DAC to a comparator, and the comparator output drives the PWM, all right, instead of a clock. And that way you can have like blanking, and you can also, the DAC has a slope function. So you can generate a slope, and you can turn things on and off, and you can do a lot of stuff. So you can generate very complex signals that you can control, like video and audio and just all kinds of stuff. You can generate signals for switch mode power supplies, and you can do a lot of stuff with it. So we'll get into that next video. And we don't have time to go to the code, the setup code for the DACs and the PWM, but we'll get into that on the next video, since it's more applicable anyway. So I think that kind of wraps it up here. So I will see you in the next video.